Hi, I'm Grace Lindsay. I'm a professor at New York University, and I'll be walking you through your tutorials today, which center on the intersection of artificial intelligence and climate change problems. Specifically, you'll be using a simple machine learning technique applied to the ClimateBench dataset. So in this first tutorial, we're going to learn about the basics of data science and machine learning. We're going to define and understand the concept of a climate model emulator, which is what you will be building today. And we're going to introduce the ClimateBench dataset, and you'll be visualizing some features from this dataset. So let's start with our understanding of data science and machine learning as a field. Data science is a field that uses math and coding to visualize, analyze, and find patterns in diverse data sets. It's an interdisciplinary field where it draws techniques from many different disciplines, but it also has applications in many different disciplines. Machine learning is a subset of artificial intelligence, so it aims to build tools that are beneficial, that can perform intelligent tasks using computers, and it uses algorithms to update parameters in models based on data. So not all artificial intelligence has to be a form of machine learning, but in modern artificial intelligence, basically everything is the result of machine learning. So let's learn some basics about machine learning. There are different types of problems in machine learning. The first is a regression problem, and this means you're trying to predict a numerical value based on inputs. So for example, maybe we want to be able to understand the relationship between increases in temperature and sea level rise. And so we might want to be able to predict sea level rise in meters as a function of temperature in degrees. We can also see classification problems in machine learning. So maybe we want to be able to classify if a certain region is in a specific season, and we could use something like temperature or a combination of temperature and precipitation as inputs, and the output would be a discrete label like winter or summer rather than a number. And there are also control problems in machine learning. So these are a little bit more complicated, but they involve predicting the best action to take within a dynamic environment. So you can imagine the algorithm that's responsible for controlling the flight of a drone needs to be able to control the drone and predict what the best action to take is to keep the drone in the air and on its right path. So let's talk about the learning part of machine learning. So in machine learning, you have free parameters in the model. So if we look at this case here of just a simple linear regression equation, we want to be able to predict sea level rise based on temperature. So let's say sea level rise is the y here, temperature is the x. And basically in linear regression, you're just trying to fit a line to the data points and say, what is the line that best describes this? And a line can be defined by the slope here. So this value beta is what we need to determine. What should that value be? And we can see three different options here for the slope. And so the question is, what is the value of beta? What should it be based on these data points that we have? So the value of beta is a free parameter in the model, and the learning algorithm needs to figure out how to set that free parameter. So that's what the learning algorithm in a machine learning model does, is it is a way of determining what values these free parameters should take. In this way, the model learns how to behave from the data it is given. So once you find that beta value, you can put in new x's that aren't part of the data points that we have here and predict new y's from that. So the model has learned this relationship by setting its free parameters according to the data that it was given. So that's really great because it means that you don't have to know how to solve all the problems that you have. You can have a machine learning algorithm that is given data, and it learns from that data and it updates its own parameters, and now that algorithm, that model, has learned how to solve that problem. And so you saw examples of this in the introductory lecture about all the different ways that artificial intelligence can be applied to the SDGs, the Sustainable Development Goals, and their connection to climate change and climate change problems. So really, it's a very general purpose tool. The toolbox of machine learning can be applied to many different types of data and problems. But what you'll be building today specifically is a climate model emulator. It really builds on what you've been learning in the past few days in this course. So as you probably know, Earth system models are complex simulations that capture the interactions between the land, ocean, and atmosphere across space and time across the entire globe. And usually the globe is kind of divided into these grids, as you can see here. These models can take a long time to run. They have to run on supercomputers that fill up whole rooms, and even with these very large computers, these models are so detailed and complex that they can take days, weeks, even longer to be able to simulate the climate into the future. But these models are really important because we can use them to help understand what will happen if we choose to take different paths. So for example, the shared socioeconomic pathways, the SSPs, are these predefined options in terms of the emissions that we choose to emit over the coming years. And so you can see here a plot of past emissions, CO2 emissions, the CO2 concentration, and you can see these different SSPs corresponding to kind of different choices society could make that would lead to different concentrations of CO2 in the atmosphere. And so by having these kinds of possible pathways and putting them into a climate simulation model, you can see how the temperature would be expected to change under these different pathways. And so these are kind of ways of building out hypotheticals and knowing what will happen in the future based on the actions that we take. And so in that way, they're very important. These climate simulation models, Earth system models, are very important for guiding policy choices in the present. However, because they're so expensive, we can't run that many different simulations. We need a long time to really kind of try out many different possible scenarios. And so emulators are models that are meant to be less computationally expensive, but still allow you to see what the outcome would be for a certain input that you give the model. And so these emulators are frequently built using machine learning so that they can learn to do the same kind of predictions that the full Earth system model does, but they can do it in a smaller, faster way so that you have the opportunity to explore more possible scenarios. And so the data you'll be working with to build your emulator today is called the ClimateBench dataset, and it was released in 2022, and it is designed specifically to help build these emulator models. So ClimateBench is designed for machine learning. It repackages the output of a specific Earth system model, the NOR ESM2 simulation. And the simulation, this NOR ESM2 simulation, was run under a variety of SSPs and also other scenarios. We're going to focus on the different SSP scenarios. And so they have the outcome of this climate model, assuming these different kind of profiles of emissions over time. And so what you'll be working with is data that includes temperature and precipitation for each location on a 2D grid across the globe. Our goal is to use the climate data, this temperature and precipitation data from 2015, plus the projected emissions profiles that are associated with each SSP to predict what temperature in a location will be in 2050. So that's what we are trying to get out of this model. That's what we want our emulator to do. So this is what it looks like. You have your inputs to your model, which are the climate data for specific locations in 2015. You have projected emissions from 2015 to 2050. You put that into the machine learning model, and it should output the temperature at that specific location in 2050. So we're going to train a model to do this transformation for us so that we don't have to run the complete Earth system model every time we want to know what would happen if we changed our emissions in a certain way. Now, before you actually start training a machine learning model, it's important to explore your data. You want to make sure that you understand what the variables in the data set mean, how they're organized, how they relate to each other, and how they're distributed. What are their actual values? So the first tutorial you'll be doing now is to load the data and build some visualizations to help you get started and make sure that you understand what you're working with. Looking forward to the rest of the day, you're going to learn how to prepare the data to be passed into models, learn how to train a specific machine learning model. We're going to talk about the concept of generalization, which is very important in machine learning, and we're going to get into the practical implications for if you try to deploy these kinds of systems in the real world.